Welcome to the deep dive. Today, we are plunging into the stack of sources you've shared with us, looking at some really fascinating cutting-edge research. We're talking about pushing the boundaries of what artificial intelligence can actually do,
Hmm,
especially when it's faced with understanding and reasoning over really long documents.
that's right. Yeah, forget just scanning a paragraph or two. We're looking at training large reasoning models, or LRMs, to grapple with just massive inputs, the kind of documents that, well, would make most of us reach for a strong coffee. Things like lengthy financial reports, dense legal texts, or, entire academic papers that just go on and on.
Okay, let's unpack this a bit. The core material here, it's from Alibaba Group, and they've been tackling a pretty major challenge. We've seen LRMs get incredibly good at complex reasoning tasks, especially with reinforcement learning, RL. But mostly, that's been on, let's say, shorter texts, maybe up to around 4,000 tokens. The big hurdle, as these sources reveal, is figuring out how to scale that impressive reasoning power to inputs that are potentially, what, 120,000 tokens long? Huge difference.
It really is. And it's not just a simple scaling problem either. The sources point out that for these long contexts, the model can't just rely on its internal knowledge, the stuff it learned during pre-training. It must actively find and integrate information directly from the long input itself. And that fundamentally changes the game for the RL training process compared to short contexts.
Right, so it's less about knowing the answer already and more like being a super intelligent detective, one who have to read the entire massive case file and actually put the clues together.
Yeah.
And these researchers didn't just, identify the problem. They've proposed a novel framework. It's called QwenLong-L1, designed to try and solve it. We're going to dive into the specific issues they ran into with this long context RL training and explore the clever solutions they've engineered within this framework. Get ready for some potentially surprising insights into how these models might learn to think in a deeper, maybe more deliberate way.
So let's maybe pinpoint the exact challenges of applying RL to these massive documents. As you mentioned, RL has been quite effective for short context reasoning, but stretching that to 120,000 tokens, that introduces some significant, well, headaches.
Yeah, what makes it so much harder? Is it just the size?
Size is part of it, but it's more nuanced. For short tasks, the model has a smaller search space for relevant info within the text, right? And it can lean more on its vast pre-trained knowledge. But with long documents, it's really all about grounding. The model has to locate the specific relevant pieces of information scattered throughout that huge text, and then use only that information, often combined in pretty complex ways, to reason and arrive at an answer.
Right, it has to filter out all the noise, all the irrelevant stuff, and just focus on what's actually important. That sounds incredibly difficult.
It is. And the sources highlight two main issues they faced when trying to apply standard RL methods here. First, they observed suboptimal training efficiency. Basically, the model's performance, measured by the reward it gets for correct answers, it improved much, much slower.
Slower progress. Okay, why was that happening, though?
Well, they found that when dealing with the long outputs needed for this complex, long context reasoning, the model's output entropy, which is basically, the diversity of its potential responses, it reduced faster. And this limited its ability to explore different paths or strategies to find the right answer. It essentially got stuck in less effective approaches sooner.
Okay, so limited exploration means slower learning. Makes sense. What was the second big challenge then?
Unstable optimization. The training process itself became much more volatile. You'd see performance scores fluctuating significantly rather than smoothly improving. Bit of a roller coaster. And this instability, they attribute it to the much greater variance inherent in evaluating responses derived from these very long inputs. It's just harder to get a consistent, stable learning signal when the source material is so vast.
Slower progress and a rockier training path. Yeah, it definitely sounds like you need a new approach. So how does this QwenLong-L1 framework actually tackle these problems?
Right, so QwenLong-L1 is designed as this novel RL framework specifically to guide this difficult transition, taking models that were initially good at shorter tasks and adapting them using a method they call progressive context scaling during the RL training itself.
Okay, progressive context scaling. That sounds like you're gradually increasing the difficulty, maybe.
Exactly, but it's not just that one idea alone. This is where it gets really interesting. The framework has three core components that work together, all outlined in the research.
Okay, lay them out for us. What are they?
First up, there's a crucial warm-up phase using supervised fine-tuning, or SFT. Before they even start the reinforcement learning part, the model goes through an SFT stage. And this is specifically designed to build a solid initial policy for handling longer inputs. It's about giving the model a basic foundation and, importantly, stability when processing these large amounts of text.
So you teach it how to read and make sense of a long document before you ask it to do the really complex reasoning on that document using RL. Is that the idea?
Kind of like that, yeah. It provides a much more stable starting point than just jumping straight into RL, which could be chaotic. The second component is curriculum-guided phased RL. Instead of trying to train on the full 120,000 token context from day one, which would be overwhelming, the RL training is actually divided into phases, and each phase gradually increases the input context length the model has to deal with. This phased approach makes the whole adaptation process much more stable.
Ah, okay. So you're building up complexity over time, sort of like a workout plan where you increase the weight gradually, maybe?
Precisely. It's all about managing that difficulty curve. And the third piece is difficulty-aware retrospective sampling. This one's quite clever. It involves pulling challenging examples from the earlier, shorter context training phases and reincorporating them into the later, longer context training stages.
Wait, hold on. So it goes back and makes the model revisit the stuff it struggled with earlier, even when it's working on harder problems.
Yes, exactly. But with a twist. These examples aren't just random. They're weighted based on how difficult the model found them initially. Essentially, a lower initial reward means a higher difficulty weighting when it gets revisited.
Okay, so it's not just any old examples, but the ones where it really stumbled. And it focuses more on the ones it found most difficult. That's smart.
That's the idea. It's designed to ensure the model doesn't forget how to handle those tricky situations as it scales up. And it helps maintain exploration, especially around those harder problem types, preventing the policy from just collapsing into, less robust strategies. The framework also uses specific RL algorithms, they mentioned GRPO and DAPO, and a hybrid reward system, which combines strict rule-based checks with a more flexible LLM as a judge approach. This helps balance getting strictly correct answers with allowing for diverse but still valid ways of expressing those answers. That's pretty important in question answering, right?
Yeah, that hybrid reward system sounds interesting. It acknowledges that sometimes there's more than one right way to phrase something, as long as the core reasoning holds up.
Okay, so how did they actually test if all these pieces, came together effectively?
Well, they focused on document question answering, or DocUA. And this is a really good test case because it absolutely demands both finding specific information buried deep within a long text and performing multi-step reasoning based on that information.
You can't just highlight the right sentence. You have to actually understand the sentences and combine ideas from different parts.
Exactly. And to evaluate this, they built their own dataset called DocUA RL 1.6K. It was specifically designed with problems requiring math, logic, and multi-hop reasoning, all spread across long documents. Then they put QwenLong-L1 to the test, using R1 DistillQuen as the base model. And they compared its performance against a whole range of leading models, proprietary ones, open source ones, across 7 different docu benchmarks.
Okay, the moment of truth. What did the results show? Did this framework actually give them a significant boost in performance? They saw some pretty compelling results, yeah. First off, just doing long context SFT alone, that warm-up phase, it showed pretty limited performance gains and was quite inconsistent across the different benchmarks.
So that initial warm-up helps, but it's clearly not the full solution on its own.
Not by itself or getting to peak performance, no. But integrating RL through the QwenLong-L1 framework, that showed significant improvements. The QwenLong-L1 32B model, for instance, gained an average of 5.1 points over its base model across all those benchmarks.
5 points on average. That's a really substantial jump in performance metrics like these.
It is, yeah, it's a big deal. And when they stacked it up against other state-of-the-art models, QwenLong-L1 32B performed comparably to Claude 3.7 Sonnet Thinking, which is impressive. And it actually surpassed others like OpenAI O3 Mini and even the larger Qwen 3235B A22B on these specific long context tasks.
Wow. Okay. So this training framework is capable of taking a, let's say, decent base model and making it genuinely competitive with some of the most powerful models out there, at least for this specific difficult task.
Exactly. And they also noted something interesting about test time scaling, allowing the model to sample multiple possible answers and then picking the best one. That further boosted performance, which suggests the RL training isn't just finding one answer, it's helping the model explore a wider space of potentially correct solutions it can then leverage.
Right. The ablation studies are often where you really figure out the why behind the results, aren't they? What happened when they started removing parts of the QwenLong-L1 framework?
Good question. Removing that warm-up SFT phase, that significantly hurt performance and, interestingly, made the training much less stable. They saw higher gradient norms. This really confirms that SFT is pretty essential for giving the RL process a solid, stable foundation to build upon.
So you absolutely need that initial base training on long context before you try to reinforce the reasoning part.
Seems like it, yes. And training with a naive single-stage RL approach, just throwing the full long context at it without the curriculum-guided phases, that was much less stable too. The training dynamics fluctuated a lot more, as we discussed earlier.
Okay, so the phased approach is crucial for managing that complexity and keeping the training on track. What about that difficulty-aware sampling? Did that make a difference?
It did. That also proved important. When they took out the difficulty-aware retrospective sampling, performance dropped, and they saw the model's policy entropy, its exploration capability, decrease faster in the later phases. This is key because it shows that revisiting those hard examples actively helps maintain exploration. It stops the model from converging too quickly on potentially suboptimal strategies.
Hmm. Really seems like every piece of that framework is there for a specific, necessary reason to handle the sheer difficulty of these long contexts.
That's a key takeaway, I think. They also did a deeper analysis, digging into the roles of SFT versus RL. And interestingly, they found that while training a model only with long context, SFT can be efficient and get you, acceptable performance. Applying RL after that long context, SFT only resulted in pretty marginal improvements. Not much gain.
Wait, really? So doing a lot of SFT on long documents before RL wasn't actually that helpful for the RL stage? That seems counterintuitive.
It does, but their analysis suggests SFT and RL play different complementary roles. SFT helps the model learn to imitate the patterns and structure of good answers based on the training data. It gets the model performing acceptably, looking good on the surface. But RL, which focuses on maximizing a reward for getting the correct outcome, seems necessary for unlocking optimal performance. They actually theorize that excessive long context SFT might train the model into a kind of local optimum. Pretty good solution, sure, but one that's hard for RL to then break out of to find an even better one.
Ah, okay. So SFT teaches it to sound like it's reasoning well, like mimicking the examples,
Yes.
while RL teaches it what actually works to get the right answer, even if the process maybe looks a bit different sometimes.
Exactly, that's a great way to put it. And they backed this up by analyzing the model's internal reasoning behaviors. They looked for evidence of things like grounding, finding the relevant info in the text, sub-goal setting, breaking down complex problems into smaller steps, backtracking, revising an approach if it's not working, and verification, basically checking its own work as it goes.
Okay, like actually seeing the steps it takes internally to solve a problem, not just the final answer.
Yes. And they found that RL training progressively increased the frequency and sophistication of these reasoning behaviors. And crucially, this increase correlated directly with the performance gains they saw. Now, SFT also increased these behaviors to some extent, but it didn't translate to the same performance jump, which really reinforces this idea that SFT might be teaching the surface appearance of reasoning, while RL is cultivating the actual underlying processes needed to successfully solve these complex long context problems.
That distinction is really powerful, isn't it? It makes me think about, well, teaching humans. You can show someone how to solve a problem, give them the steps, but they don't truly understand it until they practice it themselves, make mistakes, get feedback, and figure out what steps actually lead to the correct result through trial and error.
It's a strong analogy, yeah. And the case studies they included in the paper really illustrate this difference nicely. In one example, the task involved extracting specific financial details from a long document and performing a calculation. The base model and even an SFT-trained model got totally distracted by irrelevant financial information elsewhere in the document. The SFT model even got stuck in a loop, apparently, and hit its token limit just trying to parse all the noise.
Just total information overload, and it couldn't filter effectively.
Exactly. But the QwenLong-L1 model, the one trained with their full framework, while it initially got distracted too, it managed to use what looked like internal self-reflection, those verification and backtracking behaviors we talked about, to filter out the irrelevant details and correctly identify the information needed for the answer.
Wow, it course corrected in real time based on its own sort of internal evaluation. That's fascinating.
It is. And in another case study, it required calculating interest over 2 years from some really dense legal filings. The QwenLong-L1 model successfully navigated the complex text and performed the correct multi-step calculation, came out to $980,000. And they showed how it clearly exhibited multiple reasoning behaviors along the way, grounding the numbers in the text, backtracking when it hit a dead end, verifying its intermediate steps. It really demonstrated how these internal cognitive steps, fostered by the RL training, enabled it to solve a problem that requires deep, careful engagement with the document.
Seeing that process unfold, even conceptually, makes it much clearer that it's not just a lucky guess or a simple pattern match. It's the development of a more sophisticated, robust problem-solving strategy.
Precisely, that's the key difference they're highlighting.
So, wrapping this up, what does all this tell us? This deep dive into QwenLong-L1, it really underscores a crucial point, I think. Getting AI to genuinely understand and reason over these massive amounts of text isn't simply about scaling up the model size, throwing more parameters at it. It seems fundamentally about how you train it, and particularly how you leverage reinforcement learning in a very structured, careful way.
Yeah, that combination of progressive context scaling, the intelligent sampling of difficult examples, that foundational SFT phase, and then the careful application of RL. That
Yeah.
seems to be the secret sauce here.
And the insight that RL appears to cultivate deeper, more effective reasoning behaviors compared to SFT's potentially more superficial, imitative approach. That's incredibly compelling. It's a real window into how these complex models might actually learn to think in a way that leads to demonstrably better results on genuinely hard tasks.
Absolutely. And the sources definitely point to exciting future directions. Things like scaling these methods to even more diverse and complex real-world tasks, exploring new architectures, maybe even better suited for incredibly long or potentially infinite contexts, and just refining these RL training paradigms further. There's still a lot to explore.
This work feels like a significant leap towards creating LRMs that can genuinely ground themselves in dense, information-rich environments and reason robustly, essentially becoming powerful AI assistants capable of helping us, digest and understand vast amounts of complex information that we just can't process on our own.
Moving beyond just finding keywords, yeah, towards something closer to true comprehension and analysis.
Exactly. So here's a final thought for you, our listeners, to mull over. If reinforcement learning, which fundamentally relies on trial, error, feedback, and achieving a desired outcome, if that's proving crucial for unlocking these deeper reasoning capabilities needed to handle complex, long-context information, what does that suggest about the potential for AI to move beyond just sophisticated pattern matching towards something that starts to look, well, a lot of like genuine understanding and problem solving?